This recording will show you how to set up and run the VTAS version 3.6 executable on your Windows 7 machine. First, as you can see, we have the VTAS version 3.6 zip file on the desktop. So if you double click that, you'll see you have the VTAS version 3.6 folder. What we want to do is take that folder and put that on the desktop. So you can see now it shows up as a folder. If you go into the folder, you can see there's a large number of files in here. The most important file, obviously, is the application file. This is vtas.exe. You can see there's a manual here. I encourage you to take a look through the manual. The manual provides a lot of information regarding the text-driven input that you find in the input deck. What I'll show you here in a minute is how to use the graphical user interface in order to set up and run your VTAS files, but I highly encourage you to look through the input deck and get to know how to use the input deck. This is much more flexible, and there's a number of new features that are not yet in the graphical user interface that are in the input deck. Notice that there is a section here within the manual that talks about running the test suite. There are a large number of these input decks that are already available for you, and they feature a large number of different configurations and different features of the VTAS package. So what I encourage you to do is look at the one that is of most interest to you and try running that input deck, and then you can get an idea of how it works and how you can maybe modify it for your own uses. So for example, if you look at test number 22, there's an input22.txt, and of course if you look here in the VTAS version 3.6 package, there's input22.txt right here. So basically you could run input22.txt if you want to model an absorption refrigeration system integrated within the chilled water loop. So you can see the VTAS executable is located right here in the folder. If you were to double click on it, you would spawn the graphical user interface. A lot of the information that VTAS provides won't be seen because it's directed to an output window. In order to see the output, you should run the command prompt. So to do this, you go to the Start menu, type CMD, it'll bring up the command prompt. Then what you want to do is go to the current directory where your VTAS version 3.6 folder is. So in my case here, it's on the desktop. And this brings us to the folder. And sure enough, if you type dir, you can get a listing of all the files within the folder. If we were to spawn vtas.exe, or just VTAS, then you can see the splash window pops up. And then you can see that some information shows up on the command window, notably the run date and time, the version number, the version date, and the working directory. So this is the starting screen for VTAS through the graphical user interface. What we could do is you could start a new simulation from scratch, or you could open an existing one of these files that I told you from the test suite. What we'll do is, for simplicity's sake, we'll open an existing file, and we'll open up the first sample input deck for you, which is input1.txt. You have a couple different options here. You can cancel and go back to the first screen. You can open up the file and then modify the file by going through the graphical user interface windows, or you can simply open and run it and skip to the end of all the windows. So here we'll open and run it. It takes it to an input check, and it basically looks at all of the input parameters you provided to make sure that there's no red flags. This isn't an all-inclusive check, but it does check for the major issues that you can potentially have. Click on Next, and it brings up the list system layout window. In the system layout window, you can see that you have the components themselves of the data center, the CRA, which is named C1, the chiller CH1, the cooling tower, which is CT1 and external, and they're all connected by fluid branches within their own independent loops. The black lines and arrows signify air, while the blue signify water. Notice that each of these branches has a number attached to them, and that corresponds to the branch number shown here. Suppose you want to clean up the organization of the layout here. Say, for example, you want to move the data center component down by 20 along the y-axis. So then you just simply say minus 20, and you have the data center component highlighted. And this is a differential, so it moves it down by 20. Say also you want to move the external component such that it lies at an x value of 30 and a y value of 20. So you can choose external from the component, choose absolute from the value. Notice this is now x and y, and we're going to put it at the point 30, 20, and remove the component. Now notice we have overlapping numbers here and arrowheads. So if we want to move and 9 away from the arrowheads 8 and 7. So first we'll take 10 and we'll move it to the right. Now notice that the arrowhead here signifies flow going from right to left. So if we choose a number closer to 0, then it'll move it closer to the cooling tower component, whereas if we choose a number closer to 1, it'll move it towards the external block. So let's say 0.3, and it'll move it back. Now for branch 9, we want to move it closer to the cooling tower to line up with 10. So instead of moving it down by 0.2, we'll move it up by 0.2. We'll say the 0.7, and now you can see it lines up with 10. So now we have a cleaner looking layout, and what we want to do then now is run it. So if we click on Next, we go to the Run screen, we'll create a text input file called infile.txt that reflects all of the inputs that were in the graphical user interface. Clicking on Go, you can see what happens here. VTAS is running on the command window, and when it's all done, the steady-state simulation shows up, and you can then choose your heat exchange or your extra destruction to be color-coded for the components on the screen here. Notice that you have different thicknesses of lines. In general, the thicknesses and the numbers next to them correspond to the mass flow rates of the fluid involved in that particular branch. The way VTAS works is by first designing a steady-state design scenario where it sizes all of the equipment such that the heat output by the IT equipment is balanced out by the cooling capacity. Then if you're interested in running a transient simulation, such as modeling a failure scenario, you can run VTAS based off of the starting point of the steady-state solution. So if we run VTAS again, then what we can do is open up the steady-state solution, which is located here in this dump file out_s.mat. So we can open up the same existing input text, input1.txt, except now we're going to hit the open button. Under the transient simulation type, you can see now the binary file name that we're going to load from is out_s.mat, which was produced during the first run. Now that we have some transient parameters, we'll choose a final step of 5 and a time step value of 1, and we can change the I/O parameters if we would like, but we're not going to do that here. And we do another input check. Notice that the layout of the components and the arrowheads is the same as in the steady state case. It was loaded up along with all the other parameters. And now when we go, you can see that we're starting to run from step 0, and we're marching through now in time. When we get to the end of the transient simulation, we have a slightly different looking output window. Now in the transient simulation, for all of the specified times, so here we have just the beginning and the end, we can plot out or color code the heat exchange and extra destruction. So at various times, we can get the values of heat exchange or extra destruction. We also have this plot dialog. The plots say the heat exchange for various components over time. So here we have a listing of all the components available to us. And if we click on one of them, it'll make a curve. In our case, there's no time variation built in through a time curve, so everything is steady. But you can see then how the heat exchange or extra destruction would have changed versus time. In our case here, the cooling tower is going to have a higher heat exchange because of the COP of the chiller. So if you're interested in seeing how the input decks work with VTAS, you can open them up using WordPad. Notice that if you were to double-click on input 1, you get something that looks very confusing to figure out how to read. And this is because the fact that MATLAB doesn't have the same return characters as used in Notepad. What we can do is if you do open with, and you can choose WordPad, you do get a much more orderly looking input deck. This is keyword-driven input, and all this does is take the values from the graphical user interface and put it into a text file like this in a form that is easy to input into the VTAS software. Notice that you can comment lines using this %sign. You can also comment in the C format by using a /* for the beginning of a region of formatting and then a */ to end that region of formatting. You have various different types of blocks here. The analysis block talks about the global parameters that you would use throughout the simulation. Notice that this is where you specify the type of simulation, steady versus transient, and also some solution parameters. You can define servers individually. These are types of servers. Notice that each server you should specify a fan with it and a heat output. For racks, what you're doing is providing groups of servers, And you're also providing fan curves that correspond to the server fans, whether or not the server fans are going to increase or decrease in flow rate over time, and also the heat output of the servers themselves. There's also an additional line for the heat put out by the non-server equipment on the rack. And this rack R1 is, just like the server, is only a type of rack. This isn't a rack actually placed in the data center. To place a rack in the data center, then what you want to do is define individual rows in the data center block, and you're putting a group of racks type R1. In our case here, we have one row in the data center, and it contains 3 racks type R1, which are specified up here. Also, for each row, you specify a supply heat index, or SHI parameter. This will dictate the flow within the data center. If you'd like, you can also specify the flow bypass parameter, which is the amount of air within the cold aisle that goes to the return plenum directly instead of through the rack. You can also specify the amount of heat that's put out by the non-rack equipment within the data center, and provide a time curve with that, and other dimensions within the airspace of the data center. You can define here one CRA unit. Notice that you have this level keyword. So there's different types of levels of complexity associated with some of these components. Some component models are more advanced than others, and generally the higher the level, the more advanced the component model is. A level 1 CRA is a very simple cross-flow heat exchanger where the air side is mixed and the water side is not mixed. An effectiveness NTU calculation is used to determine the heat exchange and the entropy destruction within the CRA. Here, the chiller, we have the default value of a level 1 chiller, and in the chiller it's just a fixed COP value, so it's very simple. Here, the cooling tower model is also level 1 because the default level for all the components is level 1. And here the temperature of 20 degrees C specifies the output water temperature of the cooling tower going back to the chillers. You can also specify external conditions surrounding the data center. Here we're specifying the T external and RH external, a temperature of 20 degrees C and a relative humidity of 50%. VTAS has the ability to grab data for specific locations and allow you to even model transiently how this data center would behave under the changing conditions of a given location. We have climate data from over 1,000 locations from the National Institute of Standard Technology, and the data we have is hourly data taken over a typical year. This data includes the temperature and relative humidity. You can specify flow loops as well in the data center to connect all the components together. There's a lot of complexity here, but briefly, branches connect the components together, and the branches must close out. So in other words, we have a loop going from the cross C1 to the data center and back. Therefore, each component in the loop has one branch going into it and one branch going out of it, so the loop is closed. And this is a requirement in order for your system to behave appropriately. Same thing with the chilled water loop. A very simple chilled water loop. We have water going from the chiller to the CRA and then back. Condenser water loop, same idea. We have going from the cooling tower to the chiller and then back to the cooling tower. Then we have a couple of outside loops that go from the external environment to the cooling tower. We have one for the air and one for the water. Notice that within these loops, you have to specify in some of these branches a fan or a pump. The lingo here is a fan and a pump are the same thing. The fan and the pump specify the mass flow rate within a given branch, and then VTAS will calculate the mass flow rates in the remaining branches of the loop. Here you specify the fans. The standard now for VTAS is that all the fans are fixed flow fans because it's the easiest approach to specify a system. Technically, you could specify a fan curve or a fixed pressure rise in the fans, but in all honesty, really the best way to approach VTAS is to provide a fixed flow rate and let VTAS calculate the pressure drop, and therefore the overall fan work and exergy destruction associated with that. If you're interested in fan curves, there is a way to specify them as shown here, but they're not really used in this particular input deck. So in case you're curious as to how to run these input decks very quickly without having to resort to the GUI, there's also command line arguments. Say, for example, going back to input22.txt, say you want to run that without going to the graphical user interface, you could just say VTAS-no GUI and input22.txt. And then if you want to provide a plot or not, you can do so. In our case here, we'll say plot off, turns off the plot. The splash window still pops up, but it doesn't enter the GUI. So we've run through the simulation now without having to go through the graphical user interface. And if you were to sort by time here, you can see that you produced a couple files. First we have out_s, which again is the MATLAB binary data file that you can use if you want to run a transit simulation. But we also have outp.txt, which is a file that provides all of the data that was produced from the VTAS analysis. So again, we're going to open this with WordPad. And now you can see we have a large number of input parameters that are being specified. But if you scroll down, you can get to the output parameters from the steady-state solution. Here, there's a POE value that's provided, along with a variety of other types of parameters that are applicable towards data centers. Then we have the executed instruction from each of the components here. So here you can see that the executed instruction for all the components is listed, along with the total value for the entire data center. You can see here it appears that the chiller provides the highest amount of executed instruction, followed by the direct liquid heat exchange, or cold plate system. And then here, even though it's not as useful to read, you have the branch parameters. If we were to go through and reduce the text size, and then zoom in, you can see then that all the branches are listed, the component that they're starting from, the component they're going to, the loop that they reside in, the fluid that's being used, the mass flow rate inside that branch, the temperature of the fluid in the branch, and the relative humidity. Then we also have lumps and paths information. This is more detailed than you probably need to know, but the idea is that you can break down branches into lumps and paths. So first you have a listing of lumps, and these lumps are essentially chunks of fluid that have fixed thermodynamic properties. You can see there's a fixed temperature, pressure, and relative humidity. And then there's paths. And paths have zero volume connectors between lumps that allow fluid to flow. So again, if you were to go through these and reduce the text size, you can see then that the paths have a loop designation. There's a type designation which is needed for both in the crack units. They need to specify which branch of air coming into the crack is external versus internal, and then for the chiller you need to know whether or not the water branch coming in is from the chilled water loop or the condensed water loops. And it gives the starting lump and the ending lump. Q here is a flow rate in cubic meters per second. You have any sort of gain or loss in pressure. You have an executed instruction in that path due to pressure drops. Next, there's fan pump information. So here, the fans and pumps provide information on flow, that's user specified, the pressure gain, the power consumption, and the executed instruction. Finally, there's the minimum design requirements. This is what VTAS does to size the equipment. For example, for, again, a simple cross-flow heat exchanger for the CRAW unit provides an effectiveness in NTU and an overall heat transfer conductance. So this is what's used then in the transit simulations to predict what will happen if the mass flow rates or the temperatures change. And this is true for all the equipment in the system. Notice that the absorption refrigeration units have a lot more information that's involved because it's a more complex unit. So this is just an overview of how you can use VTAS to set up and run your own data center cooling systems model. I encourage you to look through the variety of input decks that we have to offer, and I encourage you to seek out help if you have any questions.